In this video, we will be discussing linear and planar defects in crystal structures. First, let's focus on linear dislocations. So, there are two basic types of dislocations, the edge dislocations and the screw dislocations. But in reality, we can't isolate each one of them. So most materials have both have a hybrid of the edge and the screw forms, and those are called real dislocations. But to better understand, we will discuss each one specifically in this presentation. Edge dislocations can be easily visualized as an extra half plane of atoms in the lattice. So if we take a look right here, this is the extra half plane of atoms in the lattice. The dislocation is called a line defect because the locus of defect points produced in the lattice by the dislocation line is along a line. So this line runs along the top of the extra half plane. So you have here, so that just means that you have here all the atoms, if you look at sideways, and this is the dislocation plane right here. The inner atomic bonds are significantly distorted only in the immediate vicinity of the dislocation line, which it only means that as you get farther away from the dislocation line, this this distortion right here gets more and more none. It disappears. In this case, it's really easy to see, but in the next case, it's a little bit harder to identify the dislocation, which is the screw dislocation. In the screw dislocation, the motion of a screw dislocation is a result of shear stress, but the defect line movement is perpendicular to the direction of the stress, and however, the defect line movement is parallel to the atom displacement. So I'll explain that better once I go into the picture. So only a portion of the bonds are broken at any given time. So if we look at this picture here on the bottom, we can see that we can identify the half plane right here. Right here. So let's divide this molecule in half and in half. So this means that this part, the left top part was displaced in relation to the left bottom part. So what happened is this. All of these atoms were dislocated, like in this first picture on the top left, and created this edge dislocation right here. Not this edge dislocation, sorry, this screw dislocation right here. And this is a better picture of how it happened. Now, why is it called screw dislocation? Because since an entire row of atoms was displaced, if we try to follow the lines, you would always end up in the lower plane, and that is the movement of a screw. So that's why it's called screw dislocation. Now let's go into plane defects. The most common plane defect is the grain boundary. And it's the difference between the grain orientations that results in the grain boundary. Grain boundaries are characterized by their inclination and misorientation. The inclination only describes the orientation, and the misorientation describes the rotation required to align one grain with the other. So if you have something like this and something like this angle is what is required to align the two grains with one another. The less misorientation and inclination, the lower the angle of grain boundaries. Now, some very quick properties of grain boundaries is that the average grain boundary size goes up with time, and that is because the grain boundaries migrate under elevated temperatures and over time, and that reduces the grain boundary area. There are two types of grain boundaries. The first picture is a representation of the tilt grain boundary, because as you can see right here, this right here is the angle of misorientation. So this on the top is tilt grain boundary, and the one on the bottom is twist grain boundary. You have something like, so you have the line going through right here, and you have a rotation, and this is the angle of misorientation. And that covers all of the material covered in class for that's a review for the material covered in class for the linear and the planar defects in crystal structures.